And then I'm going to make the assumption you know how to put in Perl5. So a little background for you, what BC is, if you haven't heard about it. Yeah, sort of. I actually gave this talk a couple of years ago that goes through it in detail. This is something that was put together by Malcolm Beatty in order to win a prize of a 1990s laptop. It uses O.PM, so whenever you see Perl-M O equals something, you're actually invoking the something that's going to hook into Perl after it finishes compiling, so it can do some inspection. It invokes compile at the point all of the begin blocks and the compile is completed in your program. At which point, and then he also created the B module, which is the interface to finding out everything about your Perl structures and your Perl internals, so that at any given time you can understand the state. A lot of code uses B under the hood to do fancy things in Perl. BC is what I've been working on for the past year or so. And BC provides the compile subroutine that O invokes, and we use it to inspect the entire state of what's been compiled by the Perl parser, and then we turn it into arrays of C structures, which, when you rerun that C binary, kind of recreates a pseudo compiled program, at which point we just do Perl run, and it gets up and going. We also ship Perl.cc, so BC actually just generates the C file, and then Perl.cc is a helper that's used to take that C file and turn it into a compiled executable. So the old BC used a lot of tricks. It would inspect things and it would understand the state, but due to Perl not exposing certain APIs, what it had to do was it had to do tricks like GB fetch PBN, which would actually coerce Perl into making stashes on startup of that compiled binary. That makes a lot of expense, and it makes a ton of mallocs depending on the size of your program. And so what we have been working on in the past year is making it so that all of that is completely statically compiled, so that there will be almost no startup cost, so it will take up less memory. We fixed a problem with RB to GB conversion. I'll talk about that in a minute. So it really forced us to get a deep understanding of that, and I wanted to pass that along, hopefully get it recorded, so that people who want to get involved in hacking on Perl have somewhere to get started. So I'm going to give you a quick overview of Nicholas's talk from YAPC, just so that you have the basics. There's some basic data types in Perl that you need to be aware of. You've got a PV, which is effectively the equivalent of a C string, and that is. Excuse me 1 second. That's oh, there's a pen. That's typically in the form of C equals ABC, like you see here. That is null terminated, and after I think 518, it's actually got a special byte at the end that talks about cow counter. You've got IVs, so that's your integer values. So that stores things like 1 or 5 or 6 by 5 through 6. This is how you would assign it. If you do this, you're actually making a PV, not a IV. And if you have a decimal place on it, that's floating point, that's not an IV. So this is a floating point. You would do numbers like this if you wanted to store floating points. This is how you would do your assignment, and if you do something in quotes, you're actually creating an SVT PV, not a NB. There is some intermediate states like a SVT, PV, NB, which switches back and forth between it being floating type and just a string, but that's out of scope for this. So the last two are an AV, which is your array, so that's just an array of a bunch of SVs. It also has the ability to dynamically expand the size of your array, unlike in C. And then HV, which is kind of the most unique thing to Perl compared to C, and that stores your key value pairs that I'm sure many of you, or all of you, are familiar with. Okay, so now on to guts. So in order to compile a program like this, Perl has to go through a lot of steps and set up a lot of C internal structures so that this can then be run. And that's the stuff that we're going to talk about here. So the first thing that's relevant that you need to know about is the stash. So you have something called PL-dev stash. This, by the way, this is a picture from illguts, which you can find on search.cpan, but not meta-cpan for some reason. So this points to main : or actually it also points to : but that's a whole other thing. Inside of that, you can have variables in main : which might be $foo, so that would just be a basic SV. Or you have @foo, which is an AV, an array, a list. A %foo, which is an HV, or you have foo, ampersand foo, which would be a code value or a subroutine. So the way the dev stash works is if you're in main : okay, this is just a hash here. And so when you have foo here, okay, that actually points to a GV, which stores your SV or the AV that I spoke about here, your HV, etc. But then you'll see these foo : in your hash key list, and that actually points off to another package or stash. So when I get foo : you see me, I'm going into my GV, and my GV then points to another hash, which then has its own list of keys for the, in this case, package foo. That can then go the whole way through. So if you have foo bar baz, that would be main pointing to bar : or sorry, foo : pointing to bar : through that GV, and then there you would have baz with its own SV and AV and HV slot. So for the most part, you can summarize the stash as a bunch of hashes of hashes. So there's one thing I skimmed over in that initial description, is that you actually have two things. You have a GV or an RV. And this is a huge savings. So normally when you have a, if you have sub foo in your main stash, but you don't actually have any $foo or anything else, if you were using GVs, you would have to allocate the base GV, which is a SV structure, so that's 24 bytes. Then most SVs have a any structure which stores additional information. And then for a GV, it actually also points off to a GP, which is actually storing all your slots. So you can see it's 24 bytes for that, your NE is taking up 48 bytes, and then your GP is taking up an additional 80 bytes. So it's roughly 160 bytes compared to an RV, which is a special type of SV, which is what this thing here was here. And it just points through. So that means you can take up a lot less space. We learned the hard way this year that if you do, is it CV name, it actually, under the hood, coerces RVs into GVs. And that's actually one of the things we're going to be following up on later this year with Perl5 quarters, because there's actually some code that will unnecessarily coerce RVs into GVs and make Perl get bloated at runtime. So now let's talk about my and our. And this is something that initially, when I was learning Perl, kind of confused me. So an hour is actually your stash here. So if I say hour $foo, I'm referring to this stash entry here, and I'm initializing it. If I say my, I'm talking about a pad. And a pad's not stored as a hash. It's stored as an array of arrays. So you have your pad list, and the first entry is actually the name. So that's $A and $B, etc. That is in the scope that you happen to be in right now. So if I'm in the foo subroutine, the pad for it would have, and I had $A and $B, then I would have pad entries for those. So then the other items in your pad list are actually the values for $A and $B, and you can see they kind of match up, and SVs get stored in these slots. The problem is that if I call this subroutine foo recursively, well, I can't restore them in this slot. So what Perl does is it creates additional pads on demand to store those $A and $B values on the recursive calls, and then it frees it when you go out of scope. This is why one of the things David Golden talked about, the expense of entering at YAPCNA earlier this year, one of the expenses of entering new scopes is that you've got to set up new pads every time you go into those new scopes. Okay, so now let's talk about the op tree. I've heard it talked about for years, but my conclusion at this point is that I don't even know who coined the term, but there really isn't an op tree. What you actually have is you have your stash. Your stash has a lot of CVs off of it, which coming off the CV is a series of operations or ops that need to happen in each of those subroutines. There's no like monolithic tree per se for all of your operations. You do have a special CV called main CV, which is your main program that gets run when you start up. But beyond that, it's just main CV invoking other CVs eventually off of the stash. So in this case, if foo had a CV, you would it would just invoke it straight off of here. Okay, that slide does not show up well, so hopefully you can see it a little bit because I can't zoom in. I apologize. So these are your basic ops that will come off of the CV, and I'll show you how they're used in a minute. I'm going to kind of give you an overview first. You have your op, or it's also called a base op. I'm not actually clear how it's used because most of the times I see it in a tree. It's kind of at the base and it doesn't do anything. Then you have unop. The other thing about an op is it doesn't take any arguments. You have an unop, which only takes one argument, a bin op, which takes two arguments, and then a list op, which could take any number of arguments. You have a meth op. Its job is to go, based on the arguments passed to it, go figure out which subroutine or which package this subroutine you're looking for lives in. And then you also have unop aux, which at the moment I think there's an additional use, but the major use for it right now is multi-deref. And that makes it so that in prior versions of Perl, if you wanted to do foo hash key 5 and then get the array, the fifth array element, and then get hash entry big cheese, that was actually multiple ops to do each of those lookups. And what Dave Mitchell did was to make it so that all of that happens in one compact op, and it does all those lookups much faster. You also have other ops, which their job is similar to meth op, is to go find stuff. So if you're looking for $foo, SV ops job is to go find it in the stash or in the pad or wherever you happen to be and provide that on the stack for these ops up here. You have PV ops because some operations want just the string. They don't want the full SV. Maybe they're just doing read access to it, so they could care less they don't need to manipulate it per se. And then you have log ops, which are logic ops. You have PM ops, which are actually PM ops, and these do regexes, not to be confused with regex, which is a struct for regexes. You have cops, and cops are the actual line of code you happen to be on at any given point. And then you have low op. I don't know how anybody pronounces that, but anyways, that's how you do your loops. So these are the C structures, again, from gutsy. The first 4 entries, actually, 6 entries you'll see here are shared commonly across all the ops. So for any given op, like most trees start with an op, and you'll have a next, which points to the next operation it's going to do, and so on and so on. Then the other information tells the op how it's going to do whatever it needs to do for that operation. The most interesting one here is cop. Cop stores information like what line of the program this was compiled from. It has file GB, which stores for the most part, it's storing the name of the file that you came from, the stash you happen to be in at the moment, that sort of information. The stash thing can be confusing because if I have something that is an alias, I'm not actually sure that the stash is going to be accurate. So I'm not sure how that works actually. You also have warnings information. You have your hints, which I think are your stricture data. And then you also have a hints hash for the newer strict values, like when you're doing features. And that's actually kind of an array of strings that is storing other options that you have turned on in that scope you happen to be in at that moment. So this, again, from gutsy, is a picture of kind of how these ops are related to give you an idea of how they're laid out. Okay, so now let's talk about CVs. So CVs are what are holding your lead op that it's going to walk through and execute your program on. It's got a lot of stuff, and the work we've been doing the past 3 months, all of my questions are pretty much about some of these slots in the CV, and there's not a lot of people that understand this very well, so it's been a challenge for us. So almost all of so this is an SV, just like $foo or anything else, and the first slot in the SV points to an any. In this case, you have a different any for each type of variable, and this is a CV, so you have XPV CV. And these first 4 values are pretty much there for all of the different types of SVs. So you have your magic. This says stash, but it's actually magic stash, because down here you have CV stash, which is the stash the CV is living inside of. Then you have start view and root view, which is basically where that's pointing to the op that's going to be next executed when you jump into that subroutine. There's some really interesting angry code from Nick Clark from years back where he's almost certain that one of these can be eliminated, but he can never prove it. So, welcome. Okay, maybe I can talk to you later. I'd like to understand those. Anyways, you've got the pad list that scope or that CV is going to be using, and then you have outside, which is best I've been able to determine, although there's some complex rules that I still have not been able to define, points to if I am looking for $foo here and it's not in my pad, where do I go next to find $foo? So that's pointing to your outer scope. There's also outside sequence, and there's depth here, which I've made the assumption depth implies like it can't be depth on the pad, although that's what this picture is showing. But if you recursively call this CV, well, you can't update the depth. So I'm pretty sure this is a bug here. But again, we haven't been able to. It does do that? So you're manipulating the CV as you execute it. Wow. Doesn't that get you into trouble? Okay. So I talked to you guys about B modules, where you could say Perl-mo equal something. This is concise, which is one of the modules that you can do that with. This is something I stole from gutsy. And this totally ought to get put into Be Concise because it's a great cheat sheet. What it does is it explains what we're about to see. So I've got my program, and there's two ways that you can get that information. So I'm saying Perl-mo equal concise, which means it's going to, at the time it finishes compiling this program, oops. At the time you finish compiling this program here, it will hook into concise, and concise will analyze and give us this output. And then exec tells it to put it in a flat order, or if you leave exec out, you kind of get it structured here. I'm going to walk through for you what a very simple op tree does. So the first one you have is 0, and you can see here, that's your base op, or your op. Then you have semicolon, which is your cop, which is your line number information, and we can see even here it says it's on main, line 1, and the file is -e:1, I think. Then you have $. So $, is your, I'm staring at it, aren't I? Yeah. So your SV op or pad op. So its job is to go off and find the value of B and push it onto the stack. Okay? So at this point we push B onto the stack. Then this one, well, it probably doesn't have to find it. It pushes 42 onto the stack as an IB. And then we have an op. And you see that 2, so that's a bin op. And so that's going to act on B and 42. It's actually going to pop those 2 off. It's going to do the math. And it's going to push the result back onto the stack, at which point we do $. We're going to push A onto the stack. So that's A equals B. So we're going to push A onto the stack. So now we've got A and 42 on the stack, at which point we do an assign, which is going to take the A value at the top of the stack and get it and put the second value into A, 42. At which point we do leave, and I think at is probably the one that, so that's your list op, and I don't quite understand that one, but that seems to be at the end of most of these. This is a more complex version, but very much the same thing. The big difference is I'm doing foo, I'm calling foo 6 times, and you can see that we've got okay, we've got our enter iterator, so that's open squiggle, which I can't find again. So that's your LO op, and then it's doing very similar things. We push values on. I have trouble reading the exact or the non-exact version of these. So I guess we push these values on, and then this acts on those values. Or am I getting it backwards? So you're saying EX means it's optimized now? Oh, okay. But it got changed. Yeah. Okay. Okay. So now let's talk about yyparse. What yyparse does is it takes filters or the files that you have, and it pipes them through a Bison parser to actually compile your code. I'm going to read this from Wikipedia, and when I'm done, you'll understand it as well as I do. Bison is a parser generator. Bison reads a specification of context-free language, warns about any parsing ambiguities, and generates a parser which reads sequence of tokens and decides whether the sequence conforms to the syntax specified by the grammar. So basically what it does is it breaks your program into bits, and then in the compiler, each bit corresponds to, okay, I need to go off and I need to set up this entry in the stash because they're doing an hour, and over here, we're doing an assignment, so in this part of that, I need to create a couple of ops in my op tree to set those items up. So the parser is actually what builds out all of that. Okay, now on to magic. Magic is fun. We were scared of it going into it, but it's actually relatively sane logic after we got through it. So magic usually comes off your first two slots off of an SB. And what magic is a series of structs that point, it's just a linked list of structs of the different types of magic this SB has. And you have the virtual pointer, which specifies how it's supposed to behave. That's actually, for the most part, a static table that is used by Perl. And then this information is possibly how that magic is supposed to behave. The problem is every time I operate on an SB, if it's got magic, that would mean I would have to go out, peek at the magic, walk the array of link, walk the linked list, and figure out if any of the magic that's there is relevant to the operation I'm doing, whether it's a get logic. So what we do to cheat on that is back over in your SB, the SB has a series of flags that give information on that variable, and three of the flags that are updated every time you add or remove magic are your get magic, whether it's or your read magic, your set magic, whether you're writing or altering that variable, the set magic gets used, and then you have random magic, which I've never really got a straight answer of when it's used, but it's used. So these are the different types of magic. There's actually a header file that lists these out. This is from BC, how we were able, we kind of documented it to make it easier to read. So a lot of it is of type 0, so that's just your basic scalar magic, so your $zeros and $1s and those sorts of things get a 0 type magic. But then you have other things like your %sig hash elements, not the hash itself, but actually the values. Each of those has special magic on them. Let's see, ISA gets special magic. Also, anything that's tied is going to get one of these magics on it. So this is how Perl does all the special things when you assign a string to $0 and suddenly out in the process table something changed. It's because that magic had a hook in that said, okay, I need to go off and do all these other things. There are these that don't actually have detailed entries for. So all of these were PL, vtable, array length, or PL, vtable, pause. These are all entries that are just set up by Perl and available for use. There are two types of magic that are reserved for use by, as best I can tell, by XS. I'm not sure if they've ever been used. To be honest, we've never seen code that uses them yet. That doesn't mean that we're not going to blow up. Oh, and I need to talk to Liam later. But I would be curious to see how they work. You can also see, like, there's an S magic for %sig, but there's no corresponding V table. So I think that's just certain code just looks and says, oh, it's S magic, I need to do something. Right. Right. So it's just a flag for %sig. So now let's talk about Perl globals. This frustrated me for a while when I was getting started. You know, I would see PL stir tab and I'd say, oh, great, what type is it? So I'll just grep for PL stir tab. And then after much cussing, I discovered that PL stir tab wasn't actually defined anywhere. So it's defined in intervar.h. And what you see in the file is from here on over to the left, you'll see Perl bar, I, and stir tab, which corresponds to PL stir tab. And the reason it's done that way is because depending on how you compiled your Perl, whether I think multiplicity affects it, but also threads affects it. In the original Perl, what it was just a bunch of global variables in C. But then under multiplicity and under threading, what you had was basically one big, I think it's a struct. I'm going to go so far as to say it's a struct of all of these globals. And then when you create a new thread, it actually has to copy all of them into a new struct for the new thread. And so you'll see two common entries. So I now know that PL stir tab is an HV pointer. But then you'll see this, and you've got the val sequence, which is a 32-bit number. And it's also initialized on startup to 0. So we know that by looking at the 0 off in the end. Interesting globals, you've got PL stir tab, with, which we talked about. So, wait, sorry. PL dev stash, which we talked about a lot, which is your main : stash entry. But you also have PL stir tab, which is actually this very special hash, which has, well, I'll say it has no values. It only, and what it's doing is holding every single key that is in your running program. So if I have 12 hashes and they all have foo as a key, that key is actually the same value. So it kind of normalizes your keys in your running program. You also have more basic things like PLSV undef and PLSV yes and SVNo, that sort of thing. You also have things like PL stat cache. So if you do -f_, what it's actually doing is getting your stat result from stat cache so that it doesn't have to go out and do that stat or else stat again. So I'm going to very briefly go over XS and talk about that. That's its own talk. Entirely on its own. XS was originally created as an interface to system libraries because there is no such thing as a hash in C. And so if you want your XS subroutine to return a hash, you need to convert what the library gave you, the C library, into something that Perl can understand. But it was also later used and more commonly used these days for your inner loops where you need it to be super efficient. So for instance, something like JSON XS where I need to parse that tree. We have a pure version that parses JSON, but that uses a lot of ops and it's very expensive to do in pure Perl. Faster to do it in C and just get the results, spit the results back to Perl. And someone did it once, well, 4 or 5 people did it once, and now nobody else has to do it. In your CV, there is a slot for x sub, and that actually points off to the C function that gets invoked when your XS sub is invoked. There's also something called bootstrap, which gets done by XS loader, and that's what sets up all of, in this case, JSON XS, sets it up so that it's ready to run. It's what's inserting those entries into your CVs to tell it where to look for the C libraries. It can also do other stuff. This is actually stolen from BC in one of our compiled programs. In this case, we were going to bootstrap attributes in JSON XS. And I'll blow up the top subroutine up here. So it's calling it with these 4 arguments, attributes, which is a blank 10, and then we want to call it attributes bootstrap, and we want to assign it to boot underscores attributes, which is the address of the C library. So in it, we do, you have a lot of macros like DTR, which sets up a bunch of stuff for you, and then so that you don't get warnings, you have to say, well, I'm never going to use targ. Down here is the meat of it. We do this get CV of bootstrap, which is your string. It goes out and it searches for that string, which in this case would be JSON : XS : bootstrap. So it gets the address of that CV wherever it is in the stash and gives it back to you. We then flip that it's an XS sub on that CV. We put some stack information into that CV in one of its any slots in its pad list, and then we call boot on, which is that C function that we passed in to it, and that's how we go ahead and reconstitute things when we execute our binary. I thought there was more, but I think that's the end. If you guys want to find more information, I encourage you to go look at the BC talk. Also Nicholas's talk, which was the precursor to this one. Guts, I have read that 20 times, and every time I read it, I get a deeper understanding of how Perl works. Often I say, well, that's not right, and then I read it and actually realize, no, I'm wrong. I didn't understand it. Perl Guts is always a fun read. Always learn new things, and my head always hurts when I'm done. That's about it. Does anybody have questions? I expected to be corrected more, but